Next speaker is Manuel Asorey. He will talk about energy preserving boundary conditions for field theories.
Can you hear me?
Yeah, we can hear you.
I can share my screen because I have no rights to share. Can you?
Professor Kurcholu, you have to stop sharing your screen. Please.
I have stopped sharing. You have to make the speaker host, otherwise he cannot share the screen.
Yes, you have to
Manuel
make
seems
it.
to be the co-host now.
Yeah, we are trying to fix it, please.
Okay, now it works. So I'm very happy to participate in this meeting to celebrate the 85th birthday of Val. And I met him long ago, and we started to collaborate in some subjects with common interest, and still we are still collaborating in some ongoing work. So we wrote 8 papers, and as I said, there is one which is going to appear soon. So one of the subjects we have common interest was the boundary effects and edge effects in field theory. And I'm going to talk about the same subject, although not on the papers we have written in the past. So the interest in boundary effect is not only an interest in particular models, but it's a general interest in physics and life, because all of us are made of organs. Each organ has boundaries, so we have not unlimited matter. All the matter we know is limited by boundaries. So boundary effects are important in all these branches of science. But particularly in physics, even looking at physics from the global perspective, we have in cosmology and astrophysics, we have now confirmation of existence of black holes. And black holes involve surface effects. Also, we have horizons in cosmology, which again are physical boundaries in space-time. So we are forced to work in space-time with this limited amount of space-time. So this is new because in the quantum field theory is essentially formulated in Minkowski space-time without boundaries. So we have to develop new tools and new ideas to deal with these systems which are constrained by the existence of boundaries. In recent times, there have been also interest in applications to condensed matter, because as you see in the screen, the plasmons and the plasmonic in metals and dielectrics is very current fashion in condensed matter. Also, the existence of edge currents in quantum Hall effect, where Paul has been working for a long time, is also something which is of current interest. Of course, topological insulators and the appearance of Fermi arcs in wires and conductors is closely connected. The physics of this is closely connected to the gravitational anomalies, which again involves quantum field theory. So, but coming from fundamental physics, we also have boundary effects, which are more directly connected with the foundations of quantum field theory. Boundaries have a consequence, physical consequence, in the dynamics, quantum dynamics of these fields, and we do know several effects which are associated to this boundary physics, like Casimir effect, the black hole physics already mentioned, Hawking radiation, topology change, which Paul has been working a lot on this, So it's again something which involves topology to some extent is connected with boundary effects. And finally, holography, which has already been mentioned in this conference, especially in the context of the correspondence ATS CFT. But what I'm going to talk today is something more basic, is something related to the foundations of the boundary conditions in quantum field theory. This is based on a recent work made in collaboration with my student, Fernando Esquerro. And the idea is that behind the boundary conditions for the evolution of quantum field theories, there are some principles essentially related to symmetries. You know, the Nether theorem is the first place where in the derivation you involve fluctuations of the field which oscillate also on the boundary of the fixed initial and final conditions. So it's just in the derivation of the Nether theorem where these boundaries conditions are violated. So the main principle used so far to fix boundary conditions in quantum field theory is unitarity. Of course, this is symmetry, time evolution of the quantum system has to be unitary, which means that to some extent in the Hamiltonian formulation, the Hamiltonian has to be self-adjoint. But it's not the only principle, because we know that there are other symmetries which have to be also enforced, as I said, otherwise you violate the conservation of these symmetries by boundary effects. One of the interesting symmetries is the U1 symmetry of quantum field theory for charged fields. This U1 symmetry implies charge conservations on the system, Gauss law and so on. But there are systems which are neutral and they do not have this U1 symmetry, so you cannot apply the symmetry to fix the boundary conditions. And then what to do for those systems? Any system which is in relativistic quantum field theory has Poincare invariance in the Minkowski background. So this symmetry, in particular time translation and space-time translations, imply new conservations law. Time translation implies energy conservation, which to some extent is connected with unitarity. And so this is one principle which applies to all field theories, not only the ones which have a U1 symmetry, so which involve charged fields. And this is the way we were having explored it in the last years with Fernando Esquerro. Let me just take a few examples to explain how this works. So let's consider the simplest model is a real scalar field in a half space. So you have a normal Lagrangian with self-interacting Lagrangian, and due to this time and space-time translations, you have currents, four currents which are conserved, which are associated to the energy momentum tensor. So in this case, the energy momentum tensor takes this form, and in any classical solution of equation of motion satisfies this identity. So if we just concentrate in the zero component of the energy momentum tensor, we have this energy conservation law, which it means that the time derivative of energy density plus the divergence of the linear momentum density equal to zero. So in this particular case, the energy density is given by this expression, whereas the linear momentum density has the one in the bottom of the slide. First, I have to apologize because my voice is not working properly because I got a cough last 2 days ago, and so I'm still recovering. Okay. So the energy conservation law implies that the time variation of the energy contained in a bounded domain, omega, is equal to minus, there is a missing minus here in this formula, of the flux of the linear momentum across. So this is identity. And so in this sense, we say that the energy is conserved because it might change, but we understand that this change is due to the flux of the linear momentum on the boundary. Applying this conservation law to a particular case where you have half a space, the upper half a space, taking as boundary the x3 equal to 0, gives this identity where the variation of the energy in the bounded domain is equal to this integral of phi dot phi prime. Phi dot is the time derivative of the scalar field evaluated at the boundary. And phi prime is the normal derivative of this field at the boundary. So the only way of matching this condition equal to 0 is that both one of the two derivatives vanish. If the time derivative vanishes, we have a static boundary condition, and this is connected with what is the deep brain physics in string theory. The other boundary condition, so there are only two boundary conditions, which are homogeneous, so are uniform on this boundary, which is just the hyperplane x3 equal to 0. The other one is phi prime equal to 0. So it's the normal derivative of the scalar field equal to 0. This is the usual boundary condition which is used in open string theory. So there are only two choices. But if we go to complex scalar fields, the theory becomes richer, and we repeat the same scheme, and assuming translation invariance on this hyperplane, we found that there is the most general boundary condition is given by unitary matrix connecting the boundary values of the time derivative of the fields or the normal derivatives in this particular way. There is no other way out to preserve energy in the bounded domain. So this unitary matrix is belongs to U2 in this case, but because you can take the complex of this identity and you have to satisfy also another identity in that case, it means that there is an extra condition. The extra condition is that the unitary matrix is not unconstrained. It is unitary matrix which satisfy this identity together with the complex conjugate. So, in general, the boundary condition is given by unitary matrix, which also belongs to the orthogonal group O11. And this is one-dimensional. So, subgroup, which has two components, the one associated to the unitary matrix with determinant +1, and the other component is given by the unitary matrix with determinant -1. In terms of boundary conditions, the matrix, the two independent families, one-dimensional families are this one, U plus and U minus, with the parameter A and B each one, which are angle. And the explicit boundary conditions associated to this generic choice of this unitary matrix is that the normal derivative of the field at the boundary has to be proportional to the time derivative of the same field at the boundary with a constant, which is the cotangent of this angle A/2. The same happens for the G minus component. It involves combination of phi dot and phi prime, which are normal and time derivatives of the field at the boundary, and the real and imaginary parts of these combinations are satisfying some constraint equation. Particular case of these boundary conditions are for instance, when this unitary matrix is identity, of course, it satisfies all the requirements. In this case, the boundary condition you obtain is the static one. So phi dot boundary has to be 0. When this matrix is -1, it's a two-dimensional matrix, then the boundary condition is phi prime equal to 0. So this is the usual Neumann boundary condition. And there are many more which are particular. For instance, this chiral boundary condition, which corresponds to u proportional to sigma 3. And then in this case, the normal derivative and the time derivative are related by this minus I or plus I coefficient. And the same happens when you have a choice with different Pauli matrices for this unitary matrix, which is plus or minus sigma 1. And in this case, you get what is known as twisted boundary conditions, which involve real and imaginary components of the normal derivative and the time derivative of the fields. And another interesting example is the one which corresponds to sigma 2. You see sigma 3, sigma 1, sigma 2. And sigma 2 is a very particular type of boundary conditions where the real and imaginary part of the normal derivative and the real and imaginary part of the time derivative of the field are proportional. So this is an interesting example. And all of these boundary conditions give rise to different set of solutions. And in the quantum field theoretical case, you have different, for instance, Casimir energies. If you have two plates, which is the setup appropriate for discussion of the Casimir phenomena, you can repeat the procedure, but then you have a richer choice. So the unitary matrix associated to the most general boundary condition is a matrix, four-dimensional unitary matrix. So it's a matrix 4 times 4, and connects combinations of time and space and normal derivatives in both sides of the two plates and the two different sign combinations. So you have 4 independent combinations, and so your matrix is 4-dimensional. Again, there is a constraint due to the fact that this matrix has to satisfy also the same equations for the complex conjugation of the identity. So finally, the matrix which give the most general boundary condition is a matrix which belongs to a 6-dimensional subgroup of the U4, which is the subgroup given by the intersection of the unitary matrix with the orthogonal group O2, 2. And this can be generalized to higher dimensions and to more setups with different plates. And finally, the type of unitary matrix involved in these boundary conditions take this form in the case of determinant +1, and the second family, which generates the second component of the boundary conditions is obtained from the first one just by multiplying by this unitary matrix, which has determinant -1. So examples of that involve the same situations as before: Neumann at both sides, static boundary conditions at both sides, at both plates. But you have new boundary conditions, which are periodic boundary conditions connecting the two plates, and anti-periodic, and many more. But these are very well-known examples, which still preserve energy in the quantum field theory. So the interesting thing is that this approach for the scalar field is not novel, because you have charge conservation principles which give rise to similar boundary conditions. But it's very important in the case of gauge fields, because in the case of gauge fields, you don't have the possibility of using charge conservation as basic principle, because the charge conservation for gauge fields gives a tautological identity. Is why is the second Nether theorem, which doesn't helps in establishing boundary condition. So, but if we apply energy conservation to these neutral fields, as we did in the case of real scalar, to case of gauge fields, in particular electromagnetic field, you have very good foundations to formulate the theory of boundary condition. In this case, you have, for instance, the Maxwell theory. You have the energy momentum tensor, which is conserved in that case, which is well known in this form. And then again, you have the energy conservation of the energy density, which is E squared plus V squared, electric field squared plus magnetic field squared. And the momentum component is just the standard Pontryagin vector density. So the conservation of energy involves that energy is preserved in a boundary domain, in the sense that the change of energy is equal to the flux of linear momentum across the surface, as we did in the general case. So considering the particular configuration of half space, as we did in the scale field, you have that the more general boundary condition is given by a unitary matrix, which connects the tangential components of electric and magnetic fields, and an extra condition, because the electromagnetic fields are real, and then the unitary matrix has to satisfy this condition, which essentially tells you that this unitary matrix has to also belong to the O11 group. So again, we have one-dimensional group of boundary conditions with two components. The determinant plus one component is always of this form, and in practice involves a combination of a linear dependence of the components E2 and B2 of the electric and magnetic fields, and they are related to E1 and B1 of the same fields, up to a constant. And the other component is more symmetric, in the sense that it involves linear dependence of the two components of the magnetic field with the two components of the electric field, tangentials to the surface, to the boundary surface. So here you have a bunch of examples, which are, for instance, the simplest one, which is the identity, implies the vanishing of the second component of the electric and magnetic fields. And the case where this unitary matrix is -1, you have the vanishing of the first components of this electric and magnetic field. But one different case is this U plus matrix, which is proportional to sigma 3. And in that case, the two components, the two tangential components of the electric field are proportional up to a sign. And the same happens with the magnetic components. They are identical up to a sign. So this is a very interesting boundary condition, which of course implies the vanishing of the Pontryagin vector, because you have the vector product of two objects, which are the simplest, and they give zero. The product gives zero. So another case in the second component, the one which has the determinant -1, is sigma 1, where two components, so magnetic field equal to 0 on the boundary, and equal to minus sigma 1 is the electric field vanishing on the plate. And the last one, there are many others interesting, but I have to cut the list to this point. The last one I consider here is the one where U matrix is proportional to sigma 2 up to a sign. So in this case, the electric field and the magnetic field are parallel or anti-parallel. So it's obvious that in this case, the Pontryagin vector also vanishes. And this is one interesting boundary condition, and you can compute the Casimir energy with this boundary condition, and you get very different results from the previous one. So, in the case of more complex vector fields, so you have, for instance, so far we have formulated the boundary conditions in terms of electric and magnetic fields, but you can go beyond and try to formulate the boundary conditions in terms of electromagnetic potential, because you are in the Maxwell theory and everything can be formulated should be formulated for the dynamics in terms of electromagnetic potential. In this case, the first kind of boundary conditions, which are the ones which have determinant +1, imply in terms of vector potentials in the Lorentz gauge. Here we have to fix a gauge, and Lorentz gauge is very convenient because it preserves covariance. In that case, you get this type of boundary condition for the electromagnetic potential. So you have the derivative along the two dimension, which is tangential direction to the plate of the boundary, is an Hermitian matrix involving all the derivatives 1 and 3 space partial with respect to x1, partial with respect to x3, and partial with respect to time, but all of them in a self-adjoint matrix times the vector potential. So this is what you get in charged fields when you consider the current conservation, the U1 symmetry, but not for these fields, and it's quite similar, in spite of the fact that they are neutral. So for the other component, it's even more interesting because the kind of the generic boundary condition you get for this plane geometry is just that the normal derivatives of all special components of the vector potential are derived from the vector components of this potential, with again a Hermitian matrix, which involves derivatives along the tangential directions, d1 and d2, and also some time derivative in the first two components. So from this viewpoint, the energy conservation principle leads to very simple and natural boundary conditions for vector potentials derived from first principles. In the case you have two plates, again, the same can be done. The only problem is that the mathematics is more involved. You have 4 components. Your matrix is belongs to U4, but as we have been emphasizing along this talk, there is an extra condition because the vector potentials are also real functions. So the unitary matrix has to match this condition, which in fact implies that it should belong to O2, 2. So in this case, we have a 6-dimensional group of boundary conditions, and the typical geometry is that you have 2 components, one which is connected to the identity, but it can be formulated with an exponential, as we do here. It's an exponential of an Hermitian matrix. So it's unitary, of course. And the other component, which has determinant -1, is obtained from this component connected to the identity just by multiplying by parity of the matrix. And in this slide, you have the most general type of boundary conditions you can have for the 2 plates configuration engaged in electromagnetic theory with the geometry of 2 parallel plates. You can generalize this to Young-Mills theory, and it's very nice because everything preserves gauge invariance. So, but I don't have time to enter into the details. but you have the same picture. You have boundary conditions in terms of field strength components, which are, of course, have color, but the main point is that the unitary matrix should be trivial on color space, so proportional to identity, but once you impose that, the rest follows immediately. So for the, coming back to the electromagnetic case, you have some particular examples, which are quite similar to the ones for the scalar fields, but in the electromagnetic theory have a more surprising condition. So, for instance, this anti-symmetric, this zero identity zero matrix, which satisfies all the conditions, have all magnetic fields in both plates vanishing, all components, which are tangential. The same happens with this choice, with a minus sign here, for the electric field. So with this choice of boundary conditions, all electric fields vanish, or the boundary, all tangential electric fields. And finally, there is a more peculiar type of boundary condition given by the unitary matrix, which is proportional to diagonal sigma 1. And in this case, the electric field components in one plate are related with electric field components in the other plate. So E1 and E2 are the two components, tangential components in one of the plates, and E3, E4 are the tangential components in the other plate. This is our convention. The same happens for the magnetic fields. So this boundary condition implies that the fields are periodic or anti-periodic. And so you recover these natural boundary conditions by these principles. There are some conditions which are currently used in electromagnetism, which are not in this framework, but it can be obtained just by imposing extra requirements. So, for instance, if you want to have stable electronic situations on the boundary, then you have extra requirements, and with these extra requirements, you find the standard boundary conditions that appear in the literature. So I'm almost done, so let me just summarize the conclusions. First, as I emphasized at the beginning, the boundary values are essential to establish the Nether theorem, because usually in establishing Euler-Lagrange equations, you fix the boundary values at the extreme points of the fields. And to obtain the Nether theorem, you have to relax this condition. Okay, perhaps using this Schwinger approach that Marmo was telling us before, you can understand it better. The boundary conditions should be associated to conservation laws. They are not coming for free. So if you don't impose any principle, you don't have boundary conditions. You can have any arbitrary boundary condition. So you have to establish what is the principles to fix the boundary conditions, and the most reasonable one is to associate it to a conservation law. It might be a U1 symmetry, or it might be this time translation symmetry, which is the one we have been exploring with Fernando in the last year. The charge-preserving boundary conditions is very natural. It has been used in the past, but it doesn't work for neutral engaged fields, which are very important in the standard model. So the way out of this constraint is just to replace these charge-preserving boundary conditions by energy-preserving boundary conditions. And this can be implemented, I have shown, not for the case of gauge fields, but I mean, you can trust me, it works also for gauge fields, It works for any field, even fermionic fields too, with a spin not lower than 2. Reason why it doesn't work for spin 2 in the case of Maglev theory, which is gravity Einstein theory, because in this case you obtain a tautology, because the Einstein Hilbert Lagrangian, for instance, is invariant under D, and this invariance doesn't tell you that there is a conservation law, so you cannot proceed. But there is another way, which I don't have time to tell you, but which also you can get the boundary conditions for gravity. Following this principle, you have to find another symmetry, which gives you the rules to establish the right boundary conditions. And this is all. I would like to finish thanking to Val for all these years of discussions and insights and inspiration. Thank you.
Thank you, Professor Asorey, for the nice talk. We have time for questions.
Hello, Manolo. Can you hear me? This is Kumar.
Sure, yes.
Hi. Okay, I have a question regarding the first part of your talk. See, if I were to look at quantum mechanics, not say quantum field theory yet, then we know that there are examples like conformal quantum mechanics, for example, where the form of the potential can make a difference in the boundary conditions which are applicable from a unitarity point of view. So here in this discussion, I didn't understand completely, but it seems to me that the potential, at least in the scalar field part, did not play too much role in your analysis of boundary conditions. So
you are right. You are right. We discussed the case of local quantum field theories. So it means that you can you don't have singular self-interacting potentials. It's just polynomial ones, or local, and even more than local is polynomial ones. Of course, in quantum mechanics, you have more freedom because there is no this strong requirement of renovability, and then you can play with very, very singular potentials like the 1 over r squared, which is the one you perhaps have in mind. So in that case, of course, everything changes, everything. So you cannot, as you notice, everything here is driven by the kinetic. The potential part, the local part, doesn't play any role, as you already emphasized. But in the case where you have these singular potentials, Hamiltonian operator, there is also a theory, but it's not the one we have. You mentioned is not based in the symmetry principle. It's just you wish, which might be related to U1 symmetry in the Schrodinger picture.
Thanks for the nice talk, Manuel. I think you restricted to the case where there are no degrees of freedom on the boundary, which was coming from your translation invariance in the absence of boundaries. How difficult is it to just consider additional degrees of freedom in the boundary? It's natural to consider some delta function potential close to the boundary in the scalar case. It leads to boundary conditions like the normal derivative being proportional with some constant to the field.
Yeah.
Is that interesting?
So, this is a question that Val asked me many times. But in the case you are interested, you have to split your theory into theories. One which is on the bulk, the other one which is in the boundary. And you fix the bulk with the boundary conditions, but then you add degrees of freedom on the boundary, and then you have interaction between both, right? And there are many examples, and also you have been working on some of those. You know very well what's going on. But this part, which we are studying, is just the one where there is no degrees of freedom on the boundary. In fact, there is one constant degree of freedom on the boundary, but it's not very rich, as you can imagine. You would like to have more freedom of gauge fields on the boundary. So this fixes the problem for bulk dynamics and fixing the boundary conditions. To go beyond that, you have to work.
The one I had it especially in mind was the one which is natural for the functional Schrodinger equation, which is on the half line. You require
Yes.
even you require
Yes.
to renormalize the boundary conditions on the.
Yeah. Another example where this is very useful is Chern-Simons theory. Where you have in the boundary some pure Chern-Simons. You have chiral and sigma model. Is another one. Yes. But I cannot say anything from this perspective about that.
Yeah, but
Can you, yeah, okay. If I take quantum mechanics, in fact, you have worked with Alberto and Beppe, okay? And some Juan Manuel maybe. If you get an elliptic operator, which in quantum mechanics, plus let us say a smooth potential, and to find the Hamiltonian in a region with the boundary, what one gets is all unitary operators from one infinite dimensional Hilbert space you can attach at the boundary to another one, okay, which you wrote in terms of phi dot, then phi prime minus phi dot, I think, at the boundary, and the plus one. Okay, there were two Hilbert spaces, and you consider any isometry between them, and that will give you a boundary condition. Okay? And the Hamiltonian cannot change, the time evolution cannot change it because that will change the domain. And you can second quantize it. Now, this is for standard Laplacians. But what happens if you have operators with more derivatives, as you are considering, or in gauge series? This apparently does not work. There also you get a differential operator, okay, a second order differential operator, which presumably is elliptic. So what happens there?
It's hyperbolic. So you just touched the point. So my motivation for this work is exactly to answer.
But you had to go through the regime of answer.
The answer came in two steps.
So
one was down in lectures I gave in Bangalore some 5 years ago, something like that. And it was based on the imposing U1 symmetry as a rule to establishing boundary conditions. And once you do that, you obtain the same picture as the one you mentioned with Pepe and Alberto. It's just infinite dimensional unitary operators and so on. But we were frustrated by the fact that this formalism did not apply to fields or to gauge fields. And this work we have done now is the continuation. So the idea is that I focus on very simple finite dimensional unitary groups because I impose homogeneous behavior on the boundary. But if you have more general boundary, even if it is flat like this one, you do not impose translation symmetry on the boundary, then you have again the infinite dimensional unitary groups, exactly the same as in the case of quantum mechanics, exactly the same. But the boundary conditions are different because we are dealing with hyperbolic problem. You have second order differential operator, and we are not imposing hermiticity of this operator. We are imposing conservation of charge or conservation of energy, which is different. But the rest works exactly the same. So we follow the same rules. I don't know if did I answer your question properly? Well,
Maybe I'm not sure, because what I do know is that the differential operators with time included in a, say, gauge theory, that operators, the connection field is not an operator on a Hilbert space. Because of the fact that there are time-like components, it is not an
yes,
operator, it's an operator on a Klein space. But
yes,
so it is not an operator, it's not a Hilbert space operator. So I
no,
don't know whether the standard analysis of Self-Join extensions apply to such operators which act on a Klein space, indefinite metric space. I don't know. I don't know.
yeah,
I
yeah,
don't
yeah,
know if a theory.
yeah, yeah. This is what we claim. It works. So you don't have positive works.
Okay. Manolo, could I see the conclusion page that you have? Yeah, I couldn't. It's just a curious observation that you have difficulty for boundary conditions for gravity fields and also for the
Yes.
spin-one fields. It's very reminiscent of what happens with the Weinberg-Witten theorem. I was
You're
wondering,
right.
do you know any connection, or is it just completely
No,
off the
no.
wall?
One day I thought about it, but I have not found any direct connection. But it's very interesting remark, because essentially what happens with Weinberg theorem, Weinberg-Witten too, is that the problem is the massless, the infrared behavior of these particles, massless particles with higher spin. And of course, the problem is associated to the conservation laws. For instance, the energy momentum conservation law in the case of gravity is again behind the theorem by Weinberg. And here is exactly the same. So, but I don't see any connection, because I think that even if I have massive gravity models here, I do still have the same problem. You understand? It's not a matter of being massless, the particles behind the quantization of the gravitation field, but it's just a matter of having deep invariance. So it's more is deeper. So, but I could not find any direct connection between both of them. That's very interesting remark. Thank you.
Okay, I have a small question. Is there any guideline for boundary conditions in dissipative systems? Dissipative systems.
Not in this picture, but I never thought about it. But I'm pretty sure that there should be, because the essential point is that you have to determine, for instance, talking about classical field, right? You have to determine the evolution in unique way. So, for instance, if you have a second order differential operator, you have an alternative problem, which is the Cauchy problem. It's exactly boundary conditions in another way, but it's a boundary conditions problem. In fact, in our picture here, some of the choices are connected with the Cauchy problem. So you have to determine, if you want to have a well-defined dynamical system, you have to determine unique solution, provide some initial data. This data can be initial in the Cauchy sense, or can be boundary values in this picture we follow here. So you have to determine. In the case of, you mentioned, you have dissipation, so you cannot use the energy conservation law, but you still have to fix some conditions to determine unique solution of your dynamical system. And in any case, you have to determine boundary conditions associated to the dynamics of the system. I know some examples where these have been done, but they are kind of toy models. But the principles we are following do not apply in that case, because we choose exactly the opposite direction. So just enforce the energy conservation, which is in the dissipative systems, is impossible, right?
Can I speak? Manolo, ciao. This is Giorgio Mirzi.
Oh,
I was
Giorgio,
wondering,
ciao.
ciao. Ciao. I was wondering, I mean, boundary conditions are okay, but for half space. But if I think a whole space, then I have the question of reflections, which are of an interest of which have an interest of their own. If you want to impose conditions of what happens under reflections, which is very tricky in the case of gauge fields. I mean, it's trivial non-trivial, but it can be done in the case of scalar fields, but in the case of gauge fields, it gets very tricky. To say
You
nothing.
mean a space reflection, not because here we are. So in our case, we have a special plates and infinite time, so they are static, so they are forever. These boundaries, they are static. So this is a fixed picture. You're referring to that picture, no? Space-time surface, no? Sorry, a space surface. So for the scalar case, this has been solved, so there is no problem with reflection. In fact, boundary conditions sometimes solve the problem at once. You don't have to, for instance, sometimes you get some boundary conditions just by iterating some reflection procedure. But if you solve the Poisson equation, you get the solution at once, so you don't have to iterate. In the case of gauge fields, I have not looked at that because gauge fields have a special transformation under, for instance, reflection, no? But I'm pretty sure it can be done because this is adding a symmetry. Adding symmetries is good. It restricts the general setup of boundary conditions. So you have a room for restriction. But I have not looked at the problem. But what is your worry? Is that maybe...
If you want to know what I'm worried about is the fact that if you have spin-off fields, for example, and you start asking questions about tricky questions about chiral spin-off fields, you see, and then you have a reflection, and there is certainly a case in which, for example, the positivity does not work because and you know that it doesn't, but I don't know how to prove it.
Yeah.
I worried about this for a long time, but I never got anywhere.
Maybe we could continue the discussions later because we are spilled our time. Yeah. If there are no more questions, let's thank the speaker again.